David has asked a question that he's curious how you decide what can be run in parallel.
So the question is absolutely relevant. So what I wanted to answer is that parallel computing in general is used in a kind of homogeneous set of data, like I showed before. It's a Schrödinger equation applied to a kind of a very well-defined problem. So basically, the problem is divided in chunks that more or less are, let's say, equivalent in load and then distributed as soon as, let's say, one of the tasks is available to perform more workload. So in the case of a robot, we don't have this kind of homogeneity of the workload, because each sensor or each, let's say, task require different amount of time. Like, for example, computer vision in real time, like for example, the shift register. Of course, the shift register is completely useless from let's say, mobility of the robot point of view. My objective was uniquely to load the Raspberry Pi and see how much I could do at the same time. So this means that the actual granularity of the parallel model cannot just predict it upfront. I cannot just say, okay, I divided the workload in 3 tasks, 4 tasks, 5 tasks, upfront, because I don't know exactly what could be this kind of workload. So then the approach that I found and the solution that I implemented basically is the result of a number of different tests that I run, where I try to, let's say, balance not just the workload, but also the kind of task that each process was supposed to perform. And there is also another element to consider, like I mentioned before, as we increase the number of tasks, the communication latency among the different processes increase. This means that is an introduction, this is going to be an additional element of inefficiency to be considered for a proper smooth movement of the robot. What you have seen also in the video is another element. Maybe some of you may compare this robot to others that we've seen this morning, and the speed of Ulisse seems to be relatively low. The thing is, I activated the motors at only 30% of their power. So Ulisse could run much faster than that. But on one end, we have to consider that the real-time object tracking via the computer vision, and also the discrimination between object and reflection require time. And also the additional tasks that are performed on real time by the robot needs to be counterbalanced by this additional latency increase introduced by the parallel model. So what I've done in this robot, for example, is also to use a kind of configuration file to activate or deactivate the number of sensors, so that instead of running 6 processes like I shown in the model, I could run, for example, only 2. The first one with computer vision, the second one with activating the motors, and nothing else. But I could also do the rest. So the parallel model depends a lot on the nature of the computing problem that we want to solve. For example, I'm already working on next, let's say, evolution of this robot, introducing a gripper, for example, or a robotic arm to steer the camera, to increase, let's say, the range, the optical range of the camera, and search in a wider scope. So this is going to be also another interesting problem. Of course, at the end, it depends on how complex do we want to create it. But let's say this is going to be kind of a funny activity. So my goal is to create some kind of complex problem, trying to solve it with this parallel computing model.
Could you increase the amount of throughput that you were getting by adding more pies?
So that's the point. We could certainly increase the computing power, by running a cluster of pies like a parallel computer. At the end of the day, you know, each a pie is a computer in from all angles. As long as we install, let's say, the MPI for PI library for in order to run the parallel computing code, then of course we could run it. And the only limitation that I saw is that I mean, my Pi is a Model 3. So it's 1 gigahertz of CPU speed. So I don't know how fast it's gonna be the new Model 4, but of course, one of the critical problems that the Pi has is, of course, the limited computing power of the single CPU. Yep. So in that sense, for a real-time application, you know, requiring extensive computing time like object tracking is absolutely critical. And you know, for example, I also experimented not just doing object tracking with simple objects like a ball, but also, you know, face recognition, even more complex computer vision problem. But of course, the Pi has, you know, some computational limit.
Could you use like a laptop to do the computing and then pass the instructions to the Pi?
Yes,
you could.
I mean, you know, the thing is, as long as this cluster of computers, we can call it a cluster of Pi, a cluster of laptop. We could have a Cray T3E or you know, some modern parallel computing machine, high performance computing machine as well, as long as they are reachable via Wi-Fi, of course. But in that case, we also have to consider that Wi-Fi network is going to be quite a bottleneck from a computational point of view. But in principle, yes, absolutely. That's you know, what I've done is also to run my code on my cluster of laptops that I have at home. But you know, exactly because the Wi-Fi, of course, is you know, just a home connection, doesn't allow enough speed. But otherwise, it works. Absolutely.
In an ideal world, I would have cables all over the place.
Yes, of course.
Well, I think that's all the questions we've got. Thank you, Alessandro, for a fascinating look at the parallel world. So thank you very much for doing the talk and answering the questions.
Thank you very much for the invitation, and thank you very much for all these brilliant videos and demos, which are really, really inspiring. Thank you very much.
Thank you.
Bye.